Good morning, everybody. First of all, I want to thanks a lot organizer and especially Kumar and Mayank to invite me to this workshop. I'm not a chemical specialist as the previous speaker. I'm a mathematician, so in my presentation you will see a lot of equations. So I'm sorry by advance. And after I also chemical engineering, and I was born, in fact, with a coupling between computer and physics or geochemistry. Why? Because my mentor and my advisor on his PhD was Jacques Villermo. And Jacques asked me during my PhD to calculate a lot of things for his books. So I tried, and after that, I always continuing to calculate, to compute equations. So thanks to Jacques, and I know that the people here are aware about Jacques. So my talk today will be, if you want to compute, you have to know the physics. If you know the physics, you have to compute to solve your problem. So first of all, I think the coupling between computation and physics. I mentioned many physics, multi-scales, and so it should be effectively done by computing at each scale. And the knowledge will appear like that. And the problem is in total that we are, contrary to the previous speaker, quite no experience. We don't know our experience in the ground, except for some course like that. So we have to extrapolate from small cores to large square kilometers. So we need simulation. That's all. We need simulation in our activity. So to prepare which kind of simulation, which kind of work, which kind of physics work, first of all, just a glance to what could be the future of energy. We are there, okay, and we saw that the fossil energy is roughly around 80%, and the renewable energy at around 1%. In 20 years, the renewable energy should effectively grow to 10–15%. Whereas the solar should represent roughly 6, hydroscale 1, 2, 3, and biomass roughly 11. And if you take a look at the nuclear, the 6, 5, 6. The nuclear activity should be relatively stable. Before we are using effectively some activity of fusion, perhaps I know, in the after, we could effectively solve our problem of energy, but with the fission nuclear activity, so it might be stable. And if you have to take a look, the coal is decreasing, gas increasing, and oil decreasing. So you know that effectively we are going from heavy oil to light gas, in fact, such as shale gas or something like that. So, but what you have to know that even in 20 years, the fossil energy, gas and oil, will continue to represent 75% of energy. So, for an oil and gas company, we thought that we have a large area for us, and we have to work on these topics. What Total decided to go to split the kind of energy? Of course, we are continuing to go in oil, we are continuing to go in shale gas or oil shale, of course activity in the reservoir modeling, of course activity in transforming the crude oil into the final product. And after that, we decided to develop a lot of things around biomass and around solar products. This is a new activity in Total. The new branches was created last year. It's called completely dedicated to energy. Not only energy production, by solar production with the American component of sun power, but also for storage, with now the acquisition of SAFT in France and in Europe and in the US too. And also, but this is the most important thing, that we want to go in smart energies. That means we want to have the distribution. We want to distribute electricity, not only to produce, but also to distribute. So for that, what we need, you know that an oil and gas company is the resources of an oil and gas company is the share of the company. Total is a normally French company, and we are quite low oil in France. So our activity is in 130 countries, and this activity is delegated to be chosen by the NOC, the National Oil Company, to help them to found and to exploit their reservoir. And for that, what we need? We need to effectively be efficient in the queries. Of course, it's impossible to be efficient in all activities, in all types of reservoir, but we decided to go effectively very efficient in heavy oil, in EOR, that is oil recovery, and effectively in shale gas. So these third activities we are focused on to be chosen by the National Oil Company to help them to develop these activities. And so we have a lot of activities in terms of shale oil in Stanford, of a concrete research center with a lot of people of Total in Stanford to develop how is it possible for a shale, oil shale to be economic to exploit them in terms of returning, in terms of fracturing, in terms of recovering. So this activity, of course, is linked to IT performance, but mainly to numerical simulation and advanced computing. So, as I will give you some, because you know that numerical simulation is for understanding and for activity errors, so necessarily what is the underground? How is it possible to share the underground? How is it possible to find corrosion? How is it possible to exploit corrosion? So that is the activity we want to do. But the second thing of numerical simulation is also dedicated to optimization, design, construction optimization of design of field. You know that the knowledge of the underground is stochastic. So when you are discovering one field, it's for 40 years. How is it possible to have the optimal use, optimal extracting resources of this field? Because if you are pumping very much at the beginning, you have some vortex and there are no oil after, let's say, 2 years. So that is a very important thing that we are using HPC also for optimization. So the benefit is classical, but this is very, very, very important, especially in the industry. As I mentioned, that computing is one thing, but it's never, it's unuseful, it's not linked with physics. It's not linked. So if you want to go further, if you want to have a better understanding and so, you should work together and you should have multidisciplinary teams. It's a contrary that we did in the past. Let's say, when at the beginning, 40, 50 years ago, you have to be the expert with everything in your mind. And you are the only guide. No. Now it's completely different. You should have people with you in knowledge of computer science. You know, your knowledge is not really that. I'm not a mathematician, so people of computing science need to have numerical methods for that, numeration activities. But we need also the real physics. What is the exact equation? So, in our activity, in terms of astrophysics or geophysics or geomechanics, if you take a look to the equations, all the equations are the type I got from the hyperbolic or parabolic equations with singularities. So the real problem of our equation is to be solved at the real scale, the right scale. It's impossible to mention that, oh, it is, you could not globalize everything because you have some singularities, and singularities is not globalizing. So you have always to keep in mind that your equation should be solved at the right scale. And after that, you have to create some upscaling laws or downscaling laws, depending on what you have observed. But take this in mind. If you want to solve, you have to solve at the right scale. So for that, Total look and achieve a large computer. And we have effectively the largest computer in Europe, with actually 7 petaflopsy machine. And the objective in, let's say, I hope in 2 years, is going to up to 30 petaflopsy machine. We have to know that all oil and gas companies are exactly roughly the same computing power. And we go here is energy, aeronautics, automotive are around this one between several hundred teraflops to 1 petaflop. So the largest machine in the world is there. And for the moment, Total are the 10th largest computer in the world. But every day this is changing. Every day this is changing. So, but you saw that we are here in 2008 at 100 teraflops, and now 7 petaflops. That means, as Kumar mentioned in this introduction, the computing is really expensive. So this is the Pangea, which is a computer we have in France, compared to the largest in the world, Stan and Sequoia in Lyon. So, this slide is only to mention that the activity of numerical simulation is very wide in Total. So this is because of our Victor spice separation. And I want to insist a lot that I didn't present anything on molecular simulation for for thermodynamics, for the corrosion behavior for shell and for oil shale, thermodynamics, how is it possible to have the multi-phase and move in for refining. Of course, we have a lot of discussion this morning about freeze dead, about combustion engine and so. Chemical plants, same thing. I will present one activity in chemical plants. And specialties, you have some presentations this morning for that. So the most important thing is, if you are looking for a chemical plant, specialties, refining, and oil and gas, by the multi-scale approach, you have to recover this kind. So mesoscale, that means what could be effectively the representative element volumes of your 4 scale, of your low scales. From this point, after that, you could effectively have an analytic modeling behind that. But the first, most important thing is to what is the recover phase. So, for a company like Total, of course, we do not forget the safety. And we have a lot of activities, a lot of simulation on explosion. Deflagration to detonation, transition, and so on and so on and so on. This is very important for our team. I do not present anything on this point, but this is effectively one of the most activity in CFD. So, CFD, science space, reservoir modeling, chemical plants, activities for compounds in terms of activities or instance of estimated compounds. Activities also here on catalyst. Activities here on corrosion, on adhesion of metal, on plastics. So, right everywhere we need simulation. Why? The numerical simulation and HPC, why it is an innovative tool? coupling activities, physics and electricity. First thing, we could develop more accurate physical modeling. Because we have most information, we can to solve directly the by DNS computation on some part of the activities, at the low scale, of course. We could increase the accuracy of the modeling of physics. That's the first point. Second point, of course, we could effectively have better numerical methods, with better numerical shape. And the third point is the majority of activities of Total are stochastic. They are quite nothing deterministic. We don't know exactly. We don't know reactor. We don't know an industrial reactor. We don't know what is the underground exactly. Quite often, we have to solve what we call an inverse problem. We have some data, and we have to solve what is exactly the inside of the system. So we should effectively estimate something. And HPC is one way to go to robust optimization, to robust knowledge. And for that, for stochastic, using stochastics method, stochastic programming. So I will only speak about 4 activities if I have time. I don't know if I intend to describe everything, but I try to go to seismics, resonance simulation, what is important for us, in-situ data processing, and for the one experiment of multi-phase, multi-scale reactors. First, seismics. The seismics with the wave equation is typical of inverse problem. So, what is the I think what can I? So, could you please point on the point on this one? What's that? Yeah, could you put the point on this one? This is a movie. Wait. Yes, this one. Oh. So, okay. Okay. Then no movie. So, no, okay. I forgot to use the movie. So, it's not very important. So, this is a small movie to understand what is the generation of oil in the underground during 100 million years. So, for that, what is the seismics? We are using effectively one activity to send the crash of certain frequencies, and we have a lot of receiver behind the boat. In this case, we have roughly 50,000 receivers. That means you saw before, doing this kind of activity. This wave is only from one direction. This is what we call the WAZ. That means that we have shown the describing of the waves on a large area. And this is what we've done today. This is a completely full seismic. That means when you are effectively just about there, you could recover everything around these activities. Of course, this is roughly 10 million, and this is roughly 200 million dollars for that. Okay, and the generation effectively, you recover this one. This is the activity, you recover this block, for example. This is a block of 7,000 square kilometers. This is the west of Africa, in fact. And this, you recover exactly this, what we call the seismic tube. This seismic tube is data coming from each receiver. And the scale and the mesh of this data is roughly 5 meters. That means the amount of data, of seismic data, is in this case roughly 200 terabytes. Each time you have to solve a seismic campaign, we have to use 200 terabytes. And Kumar mentioned in this morning that physics and data should be coupled. This is the best example for that. We know the wave equation, so far. We observe this effectively like a echography of the underground, exactly. And now we have to solve. So we transform this activity frequency domain. We are using an algorithm which we call the RTM, reverse time migration, because the first data are waves, okay? Equation of the waves. So we have to transform the energy in the wave to a picture. That means what is exactly the underground at this scale. So we have to change the vertical scale to pass from an image to a real image of the basement. So this is called for which algorithm we call reverse time migration. Reverse time migration is simple, and we will see that HPC could effectively improve the accuracy. So it's a finite element method. It's a 4D wave field, injection and backpropagation of the data, and the sum of correlation gives an estimate. And this is the result. This is the result for one way and two way. And you see, if you are effectively using only one way integration and two ways, you see that this picture is clearly very much more information in this picture than in this one. So, clearly, this is the activity of the time migration. First, you have the burden shaft, you have recovered that, and after, you have the receiver there. And we will recover exactly the superposition of each when we receive. So, I will skip. Right? So, you understand that effectively each wave is quite independent from one to the other, but dedicated quite to the same space. So, this activity of systems is clearly, potentially, massively parallel systems. So the first application in total of HPC is effectively this application of seismic. You have to solve the wave equation there. That's too complicated for the moment. We solve only the Helmholtz equation. This is an hyperbolic, and Helmholtz is an elliptic equation. And effectively, we could effectively split all the knowledge in frequency domain, as I mentioned previously, and in all frequency domain, we could have a Fourier transform with a shift of phases. We inverse effectively. We have effectively a lens correction and right angle correction. And after that, we have an imaging condition. It's impossible to parallelize everything like that. So the 7 petaflopic machine of Total is used for these activities. And it's completely full for that. Every day, I can mention that the use of this machine is 85% all night, all day, 7 days by week, and every week on the year. Why 85? Because we need some maintenance. So that's the reason why, effectively, I think we will effectively convince our CEO to buy a new machine in the next 2 years for 30 petaflopic machine. So effectively, we could use effectively CPU for doing that, but due to the very scalable activity, we could use also GPUs, and using GPUs effectively decrease the power consumption and they accelerate the calculations. So you understand that for this slide, it's impossible to say this guy, as you will know, in 20 years ago, for example, to understand that. So it's impossible. His knowledge is there. The first activity is how to decompose these activities. We need numeration for that. We need computer science for that. So this is really, as you see there, a real multidisciplinary team for doing it. So this is an improvement of the RTM algorithm, which is what we call the full wave inversion, FWI, at FWI. I just mentioned here the workflow. To precise, we should couple physics and data. So if you take a look, well, we start by a model, and we'll see this. We solve the wave equation, and we try effectively to compare solve equation to predicted data, and compare to observed data. And the difference is going in the model, we adjust the model, and so on and so on and so on. The reverse, the LWI, and all the activities for an inverse problem like that. You preserve the model by your physics, and you converge with the comparison of the results of this physics to the observed data. So, this is the way, knowledge. This is the model. Perhaps you don't know, but I just want to take 2 seconds for that, because the movie is not doing that. Generally, several billions years ago, you have some aquifer, and due to the magma, the aquifer is evaporated, and we observe that the salt of the aquifer, like a salt dome, and such salt dome are roughly 5,000 meters. Okay? That means if you have salt dome there, you have some chance. You have some reservoir here, you have some chance, you have some organic activities in the Miocene which is closed, because everything was built in the aquifer, the water is closed, the salt is there, so I think we thought that effectively in this area we should recover some oil. So this is the model. We adjust the model with domain decomposition, and with the results of the cubic, seismic cubic we saw 2 slides ago. We effectively compute everything, compare from this what is the result of the model to the results of the observed data in the Angela system, and go on, and convergence, and at the end, we produce this kind of image. This is effectively, this is a real image, huh? Okay? Please, I will skip that in my presentation to give you. It's a real image. It's exactly the outside of West Africa, in front of Nigeria and Guinea. This is a picture of I present the cube I presented of roughly 10,000 square kilometers and 10 kilometers of base. So we observe that in velvet, that's the color of LSU, I understood. The velvet is a salt dome. I don't know if it's a good comparison for you, but and close to the salt dome, we should find here, for example, some reservoir. And in white here, you will see the drill to recover the oil. So one way, 2 way, this is the position. I will give you the picture, but without the words. Okay, for example, if you take a look for this drill, you see that all along this Miocene there, we should recover a large reservoir. But what I want to show you that the drill there is not vertical. The drill there but it's a mixing between vertical and horizontal. So it's very complex. That way. So next, this is for classical, what you call the pulse width, classical pulse width. If you take a look now for oil shale, this is the scale of oil shale, and at the contrary of a classical pulse measure, where the oil is between 2 fails, in oil shale, the oil is inside the fail here. So we have to discover this fail, and that's not a retarting and so on and so on. But I just want to look at the future. Put this screen, this image, at the right scale. Okay. For finding oil shale, this is the scale versus classical closed region. So you understand we need more and more and more and more capacity. We need exascale. We need exascale because the scale between that and that is roughly 1,000. We need exascale. So it's not only for taking time to compute. No, it's really for understand what happened exactly in the phase. We need exascale. So physics and computing are completely linked now. The including of HPC, effectively, we have a roadmap to go to the exascale. So changing effectively our approximation of the physics, and effectively we are more realistic now. Till last 10 years we are working on the classical acoustic waves. Now we are entering in elastic waves, and we just begin the viscoelastic equations. The viscoelastic equation require roughly 100 times the same computing times. And after that, with exascale, we thought that we were going to pose viscoelastic system. So now we are representing the hybrid representation of your equation, and because we could effectively use some other physics to help us, because this image, is it the real deterministic underground of the West Africa? We don't know. We thought that this is certainly one of the most probabilistic. But we don't know if it will. Actually, to prove that is effectively the simulation is correct, we set a drill. In the 90s, 2 drills over 3 are bad. We only recovered all 1 drill over 3. Today is 85% of success. This is entirely due to the coupling between physics and SPC. But it's 85%, it's not 100%. Okay. And the cost of 1 drill is roughly $200 million. Depending. In the north, in the Arctic, is 300. In the south, close here, it could be certainly roughly more than 80. But if the average is 150 or $200 million by drill. So you understand that if we increase the accuracy of our simulation, we could save something. So now, 10 minutes, wow, I'm sorry. I have to speak a lot of it. So now, effectively, we spoke about HPC and physics. And now, because I'm a mathematician, I want to speak about numerical approaches. Because we have effectively the equation, but the most important is how is it possible to discretize this equation to be solved by a massively parallel system. And when I speak about massively parallel system, I don't know if you understand what is it. It's 100 million cores. So that means we are at the same time, you have to parallelize 100 million operations. And after that, you combine them. So it's challenging. Really, 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 really challenging, I could say. So for example, for flows, it's quite impossible. Because Darcy law or Navier-Stokes are not scalable at all. So we are using only 1,000 cores. In this case, 1 million. So for that, we have effectively we have the ability to use a different programming system, and we call generally what we call the direct acyclic graph for effectively describing what the equation could be parallel or not, and where the data for this, for example, node should be used at this one. And effectively, everything should be synchronized. If, for example, you need, for this activity, 10 times for the others. But for calculating this point, you should wait for this one. And for the wetting here, he do nothing. He's wetting. So the problem is, how is it possible to have the right schedule for each core do not wait anymore? So this is very, very, very interesting. So I will skip that, but I just want to mention that this is major activities. You could solve effectively your physics, but if you are not the right programming system for massively parallel system, you should never advance. So I prepared some slides for the numerical method work, so I just want to skip them, but only to mention that we have a large number of numerical methods to be useful. And each time it will be an improvement. So for that first atome, for example, because we are using yet the RTL in studies. So for RTL, we have to develop a final difference operators. But we want to skip absolutely final difference operator to go for Gagliardini, discontinuous Gagliardini elements with a finite element system. And we have a lot of activity on this point. In terms of optimization, effectively, as I mentioned, that we want to have the best possible stochastic modeling of the underground. So in terms of optimization, we have to work on stability, convergence, and on Gaussian field optimization, and so on. And perhaps you mentioned that this morning, Mark, that effectively the deep learning, machine learning, especially the deep learning, could certainly provide us a gradient-free optimization by a randomic approach of the solvers. So the scalability of the solvers is very important. The space domain, the complex frequency domain. So we are working on a large sparse array algebra with quality. And I just want to mention this point. In the future, we should have effectively a massively parallel system like exaflopic machine. And the exaflopic machine should effectively, the power of the machine should be around 20 to 40 megawatts. We know that 60% of this energy is consuming to transfer data. That means 60% for not computing, only for transferring data. So the objective now for the next generation of computing is communication avoiding algorithms. So that means we should effectively compute, but at the same time, we have to minimize the transfer of data. So we work on this point. So I will skip for the result. So, and I just want to present this one. Effectively, if you take a look for this activity, for the science equation, I do not explain very much, but you see the green curve here using the communication iteration versus the blue, which is absolutely no convergence, no communication iteration. You need here 250 iterations and here less than 100. So we have to continue to do this activity, and we could refer to the paper we presented and now submit it to the mathematical journal. And we hope in the future to reduce from 200 to 50. All right. So we skip this part. Except for presenting you the neural activities in terms of discontinuous Gagliardini method. We mentioned that we have some very large mesh where it's not necessary and very fine mesh which is necessary. And this is automatically done by the equations. That means here, of the equation here, we have a balance term, effectively between the minus 1, 0, and 1. That means the extension of the mesh. This is a penalty term. If you are to extend, you have a large number of penalties, so you reduce the mesh. And at the opposite, if you are too small in terms of mesh, you have a large penalty because you have nothing to do at this lowest mesh, and so you could exclude that. This is important. 1 minute on that. This is very important because my message is effectively innovative tools by coupling physics and HPC, but much more innovative by coupling physics, HPC, and data. This is corresponding to what we call the giga model in reservoir modeling. If you are looking for just a few words, that means if you are looking for this kind of reservoir here, the reservoir simulation generates roughly 350 terabytes by run, and we need roughly 41 to solve this problem. So it's too much to store, it's too much to read, etc. So we have to produce exactly the same system. During the computation, some cost should be dedicated to the data analytics. And we have to extract from this data analytics the most important features of the prediction. So that means we are only store the most important feature, extracted by statistics, volume handling, and topology. And of course, we are using much more of this activity there, of topological segmentation, by wavelets, sublinear algorithm, topological graph, and so on, and use a lot of more complex levels and functions, machine learning, and deep learning. Everything should be mixed to extract the right feature extraction and save only right feature extraction. Like that, for example. This image is used only by this storage. So we save only the graph, and we know what are the functions dedicated to this graph. This is very useful for us for the digital world properties and things. How is it possible to have the pole scale modeling of flows? I have 5 minutes, Matt.
We are for time, but yeah.
Okay.
We're running late.
Okay. So I will try to go fast.
Okay.
But I don't want to skip this one because you are effectively more chemical engineer, okay, and this is the model, this is the application we do. So this is a slow loop reactor for polishing of polyethylene. And you saw that we enter there here the ethylene production, and with the catalyst we will produce some grain like that, roughly 10 microns. And generally the bullets of polyethylene are roughly 100 microns. This is the slow problem. So this is a reality, classical, at a certain temperature. But if you increase the temperature, of course, you increase the reaction, so we will produce more. We increase the level of solid activity, more than 40%, and this is the result. All these particle aggregates and what we call the swelling part. So the reaction is, and of course, we have to stop the reaction, we have to stop the reactor, we have to dust everything. So it's absolutely crazy for production. So the objective of this research is to understand everything from the particle by itself. And you see, we describe this particle by NURBS, and we calculate all shocks and so on at the level. We are using DEM for that. I know that a lot of people are using DEM in the surgeons. And we work in collaboration with the EMS group in Beijing of Professor Jijai and this pixel. So we calculate effectively the collision of two particles. You are using the isogeometric analysis because it's impossible to have a complete mesh of the system. That to present what we are using a lot of different numerical methods. For the end modeling for the equation, we can calculate the distance by nerves between two particles. Normal equation. So to produce this reaction, then we have the propulsion mass balance and the specific transfer equation there. So we are using the two fluids only for that. Just all the equations. So for that, the two-field bundle is not building like that. It's a classical two-field bundle with the momentum and for mass transport. The specific transport equation is there. The kinetics model is there. And we are learning for this, what we call the swelling model in there. Just 2 seconds for that. What is interesting with this equation that and there is a number of the density of diameter of the swelling. That is a variation. If you are looking for, that is roughly, if you are using LBM, the PDF of the distribution of particles. Using roughly the same thing. This is effectively the hydrodynamics. GL. GL is the growth, L is the particle, GL is the growing of this particle by one particle. Okay? B, here is the agglomerate. That means you lose 2 small particles in one larger. This is B. And at the opposite, after some shocks and so on, certain particles do not aggregate but break. And B representing the explosion of a large particle in smaller one. So we could effectively adjust this equation, and what we see that the hydrodynamics could control B. That means by hydrodynamics, by the collision frequency, and by the coalescence efficiency, we could control the swelling by this equation. So now, this is the photo as it goes along. You need here. And one experience and one simulation is there. We are using a CSTO tank, and when effectively the swelling appears, the power consumption increases a lot, quite vertical. So, in terms of simulation, now you see that the apparition of swelling, and what you could see, that's effectively at 100 RPS, the swelling appears after 35 minutes. Okay? Everything is done at 40% of swelling ratio. At 200, wow, at 15, that means more than twice. And after that, we will turn into this one. That means the hydrodynamic could change completely the swelling approach. Of course, in stable side, we should recover the swelling at low rate. This is for SHR. Now, in the real loop, here we have effectively a frequency. We turn back some part of the flow from here to this point with a frequency of 7 seconds. And what you do, in the way you have the operation of swelling, and after, say, 50 seconds, the hydrodynamics could reduce largely and disappear. In this case, it completely disappears to swelling. So it's very, very necessary we recover the new frequency like that. At the contrary, without that, what you saw, that the swelling is continuing growing, and quite everywhere in the loop. This is completely different. So that means effectively, we could now show that the hydrodynamic could effectively change completely the swelling approach. Now, we have effectively experimentally proved on the Stirred tank reactor, but we are building the loop like that to provide effectively an experiment for that. So, by conclusion, I think you understand that the method simulation is very important. It's an innovative tool, but it's not one thing by itself. It's interesting and innovative if you couple HPC and method simulation with physics, with data, with numerical, with computer science. This is done effectively, I think, from my point, to explore and develop new trends. I think CFD could be useful for explanation of some classical time. But for singularities like swelling, singularities like phase in the underground, we need to have more details at different scales, and the difficulty effectively is the upscaling units. This is really innovative. And the difference in innovation is how you optimize the coupling between your activities, between your architecture of your HPC, your algorithm, and your applications. So, I want to thank HPC to mention that our activity is completely changing because we are using complete collaboration with partnership research academy by multidisciplinary team. So generally the consortium that produced and also what also is in Matthias is really multidisciplinary team, and I think that's the way for the innovation. So I want to thank you for your attention.
Now, while our next speaker gets set up for his laptop, we might take maybe one or two questions from the audience if you have quick ones.
The example which you showed. So in that case, in your opinion, what is limiting? Is the computing limiting or getting the realistic parameters for the system not limiting?
For the moment, in this case, it's never the computing limiting. The computing is the scalability of the activities.
Let's say you said you use DEM.
The DEM, we are using DEM only for 2 or 3 or 4 particles, 10 particles, not for billions. Your pleasure. For understanding at the raw level, we are using DEM, obviously, the short, how is it possible to aggregate to. But after that, we are using LBM for, certainly for massive.
The question is, how do you get the parameters for the aggregation kernel? You can write down those equations, but how do you estimate those parameters?
The estimation is when we try to find what could be effectively the scale. That is where the scale is sorry. The aggregates, the size of the aggregates could be effectively the size of the mesoscale. But the acceptable size of the aggregates, and at this stage, effectively, they are completely stable. They are not growing by the equations. So this is what we call the quantitative volume, and we are using this one for hydrodynamics.
Let's thank Philip again. Our next speaker is also from industry, Dr. Navin Lab, and he's Director for Chemical and Processes, and CDADACO is now a Siemens company, right?
That's correct.
Yeah, and another reminder, there are 10 slots still open for the hands-on CFD workshop in the afternoon, which will be happening right across where we had breakfast and coffee. So in room number 103, please sign up if you have not.
Thank you, man, for the introduction, and Professor Kumar for inviting me here. I'm from CDADACO. CDADACO was purchased by Siemens earlier in the year, and pretty soon we will be called Siemens. The name CDADACO will vanish. And if you want to know more about why and where does CDADACO fit into Siemens, please come and talk to me. I thought the two keynotes that we had today were rather interesting. I don't know if it was by design. We had a professor who was showing no equations and talking about all applied things, and we had Mr. Rekho coming from industry talking about high-performance computing, lots of equations. And I thought this was a very interesting perspective because we are normally used to other way around. What I want to talk about is again going to be applied. I'm not really going to talk about any equations. And this is the theme, essentially talking from an industry perspective. How can we get to that process design, better, faster? The life is as a whole an optimization problem. We want to be at one place and another place at the same time. We want to spend time with family and work more and so forth. And how do we get around this? Well, we are going to talk not about those philosophical problems, more about the problems in the chemical industry. And what I want to talk about is just give you a brief outline about the trends in computation, but specifically computational fluid dynamics and discrete element modeling, and how that has evolved over time, a very brief outlook on that. But then spend more time about computation for innovation. How should you compute? What should you compute? A lot of the keywords that I will be using have already been mentioned by Professor Kumar earlier, which is digital twin, 1D models such as Aspen HYSYS are not sufficient, exploring the design space, and so forth. So let's see how they, how they are applied in the examples that I have. Talking about trends, you probably realize that models are getting bigger because people want to do higher fidelity. We can create models that are up to 1 billion cells in size with ease. These are things that are becoming routine. These are not one-off instances where you can really resolve a lot of the details with very, very nice fine mesh to give robust answers, robust simulations. And that requires efficient and parallel meshing and multiple cell types. So this is something that is, I would say, past news. This is something that can be done already. Many times we will see that objects, fluid flow, particle flows, they are not stationary, they are moving. And we need to be able to resolve that effectively, whether it is dynamic fluid-body interaction or this sort of oversets that we see, or even where there are contacts involved between bodies. Those type of things are already possible as well. And then, of course, is multiphysics. Physics does not follow the whims that we have about modeling. It is governed by nature, and it has many things together, which includes multi-phase flows in pipelines and reactors, and how those flows affect structure, so fluid structure interaction. And CD Radko, as part of being Siemens, has been doing a lot of things that involve not only doing these multi-physics things, but also coupling physics from maybe two different solutions. This is an example where we used population balance method from GPROMs coupled with star CCM plus for wet granulation study, where we see that the transport of particles is modeled by discrete element method. And then as you add some liquid to it, granules are formed. You can see that the size of the granules is increasing. And here you can see how that relative mass frequency of the particle size distribution progresses as time is changing. So these are the trends that we see are happening. And what that means is you need platforms for solving these problems that can be coupled very easily. What we offer in terms of star CCM plus is in a single platform 4 different solvers, which includes doing your finite volume flow or CFD simulations, performing finite element flow using viscous and viscoelastic fluids, which are very common in the industry, discrete element modeling for particle flows, and then finite element stress and mechanical stress analysis. And these two are coupled to each other as it comes out of the box. In the same way, the finite element stress solver is coupled to the fluid flow solver. This means that setting up problems which include fluid structure interactions is as easy as it can be. And in the future, we will see that the finite element flow solver will be connected to our CFD solver to be able to do more complex multiphysics things. So as a researcher, as an academician, as an engineer in the industry, this really gives you a platform in a single environment to be able to do really multiphysics and coupled physics type of problems. When we talk about innovation, it is obviously driven by needs in the industry, and we have seen some of this explained by Philip earlier. In the chemical industry, we are looking for three types of efficiencies. One is related to energy efficiency. How can we spend less fuel, less steam? Other is related to process efficiency, in the sense that how can we have more conversion, more yield, more throughput. And finally, also related to innovation efficiency. That means Professor Ranade was talking about chemistry and chemical engineers. You invent a new chemical. How do we bring that to production? How do we scale up? How can we reduce our pilot plant time? How can we reduce our bench scale time? And all the speakers before me have already established that simulation or computation is a key in achieving that innovation. So when we talk about innovation, what do we mean by that? Obviously having good ideas. And this is one of my favorite quotes by Linus Pauling, who was one of the few Nobel laureates who received 2 Nobel Prizes, one for chemistry and I think other was for peace, if I'm not mistaken. And what he said was, the only way to have a good idea is to have a lot of ideas. Which means we need to have a lot of ideas, we need to test them, we need to validate them, we need to create that digital twin that Professor Kumar was talking about. And then at the end, we need to be able to explore the design space. What is that space that I'm working in to find that one good idea that works? Essentially the thousands of experiments that Edison did before he finally found the light bulb. And so what I want to talk about is, what has happened in the past and where we are in terms of the solutions that Siemens and CD Labco offers. Many years ago, what we call CFD 1.0, people spent a lot of time just trying to set up the model and creating the meshes and setting up boundary conditions and so forth. And at the end, what they could do was just say whether a design will work or not. Right? And then as time progressed, where we could get more reliable material properties, the cost of hardware was going down, and you could start importing your geometries from CAD directly into doing simulations. You could start doing some troubleshooting work, in the sense that if something was not working, you would do a simulation, try to reason out what is the reason, and then even out of that, start to predict, in the sense that if I had a solution, what would it be? I would do 1 simulation, 2 simulations, 3 simulations, maybe pick the best out of it and say, okay, that one looks like the one that is reasonable, which will solve my problem. What we do today is go beyond that step of validate a design or troubleshoot a design or predict a design. We go where Professor Kumar was saying, explore the design space. That means we automate the process of simulation to explore. So we are not trying to just compute, we are using computation to find out what to compute. Right? Our idea is to find that one good idea, and we start with many ideas. And so as you go from one idea to the next idea, how do you find out what next simulation am I going to do? What is my goal? What are my parameters? And how do I put together to find my best design or better design? And this is where we talk about discovering better designs faster in an automated fashion. If you look at a process, there is mixing, reaction, separation. Those are kind of the 3 basic steps. Siemens or CD Labco makes tools which allow you to even optimize a process on a plant scale level. This is the 1D or higher level that Professor Kumar talked about earlier, where we can use an optimization tool around a typical process simulation package. This is the example that we are talking about. We have 2 locations where steam is being added, and there is certain effluent that is coming out, dichloromethane. And the goal was, how can I minimize my steam consumption by varying ratios of my feed with a certain condition that the effluent concentration should be less than 150 parts per million. And as a result of running this simulation repeatedly, but in an automated fashion, what we see going from the baseline design to input design is a significant amount of savings in the total steam that is consumed, while we still are within the range specified as our constraint. So this is possible not only for a simple process level simulation, but also for computational fluid dynamics. Stirred vessels, though not the best type of reactors, are still commonly used. They probably will be used for at least some years to come, many years to come, for decades to come. And the question, for example, if we say that I want to find a design that I maintain my blend time in the reactor, but reduces my power consumption, how would you do it? Professor Ranade earlier used the word we came up with a design. And came up with means I did one simulation and the second simulation and the third simulation, of course, based on my experience and what we know about transport phenomena. But then how do I know which one to do the next and how many should I do? Right? So that's why I said we are going to use computation to find out which computation to do. So this is a simple example. When we set the simulation up one time, we tell what the variables are. I tell it that we could go from 2 levels to 3 levels of impellers. We can change the angles of our blade. We can introduce baffles or remove baffles, with the goal that I want to reduce my power consumption. And this is showing you the number of designs. And this is running on its own, where we use optimization algorithms to exactly do that. I want to find out what is the next design that I should evaluate. And then Philippe from Total already talked about high-performance computing. So this is where running all those designs using high-performance computing comes into picture, where we go from a baseline to an improved design, which had a 4-fold decrease in power consumption while still maintaining a blend time. This is where we see a lot of our users innovating. Okay? Not for just simple designs, but also for complex designs, where we start building the model virtually, testing it in the sense to see if the physics works, going finally to assessing it, and then in the end, do a complete design space exploration study to find out, how can I reduce my temperature difference. And here we are seeing all the designs that are being explored. So here, the temperature variation at the back end of this static mixer. Let me give you another example. This is for a process burner. Now in this case, the physics is not simple. We are talking about combustion, we are talking about radiation, we are talking about calculation of CO and NOx that is coming out. And what we are doing is automatically changing the designs of these burner tapes, the angles between them, in order to satisfy certain conditions. That is, my heat flux should be uniform. And I want to reduce my NOx and CO that is produced by the burners. And here is what we see. We start from baseline of CO and NOx, which is on the x-axis. And from there, I go to a design with minimum possible NOx and CO. And as chemical engineers, you probably know that NOx and CO are quantities that are counteractive. That means one goes up if the other goes down. But with the help of automated design space exploration, we are able to explore those designs, which otherwise would be almost impossible if you try to do that manually. How much time do I left? Okay. Okay, I'm right on time. This is my summary. Of course, we need experts on tools and process development, such as the bright students that we probably have at LSU in developing those models. And then we need to create sort of these good citizens of the Republic of Computation, if you will. And what does that mean is, in the past what has happened, we would have a few people who were real experts in computation, and then we had engineers who were doing their daily engineering life, but were not much exposed to computation. And there is a big gap between the two. Companies like CD Radco are now part of Siemens, our attempt is to bridge that gap where we see that not only there are experts, but there are people who can apply that computation in their daily engineering jobs. And then finally, of course, design space exploration and HPC is going to play a big role in innovation, to bringing all that was discovered or developed at universities and academicians using data, using innovative models, can be translated into practical solutions for the industry. So with that, I will stop. If there are questions, I'm here to answer those. We do have the workshop that Professor Tyagi already mentioned, which is the room right next door. So there are quite a few spaces that are left. If you would like to come, join, see more examples, applied examples of how design space exploration works. And at the same time, we'll also have a hands-on session. So you'll be able to put your hands on at least a simple problem to see alive how that design space exploration works. Thank you very much.
As he has already mentioned, you can actually have longer discussion with the CDA folks at 10:34. If there is a quick question while next speaker is setting up his presentation, you may ask it now. It's a great pleasure to actually have Professor Benjamin. He's lead PI for the project that intern dean Professor Bondak was mentioning about by materials, 3D manufacturing and materials.
Additive manufacturing and multi-scale metal forming.
It's a mouthful.
But I think what's in will be much better, so I'll talk about that.
Okay. Thank you. So, my assignment this morning, I thought, was to actually give the audience here at least an impression of the recently awarded program to the state of Louisiana from the NSF as for all workers. This is a statewide program to establish what's called the Consortium for Innovation in Manufacturing and Material Synth. While LSU is the lead institution, there are in fact 5 academic institutions within the state that participate in this program. Over the time period from 2015 to 2020, the project is funded at $20 million. Very briefly, the state put together an effort to develop this proposal to the National Science Foundation in 2014. The official award was made in 2015. The project is directed from the state export office by Professor Ansari, and the scientific investigators come from a partnership between LSU College of Engineering and College of Science, as well as from Louisiana Tech and Southern University. The project focus, the scientific and technology focus of the program, is actually looking at advanced manufacturing and associated materials problems for metals and alloys. 2 so-called science and technology thrust areas. One is what we call multi-scale metal forming and pattern verification. One is talking about material design, processing, and characterization for 3D-based metal printing. In addition to these 2 STTs, we are actually charged to develop data and what's called integrated computational materials engineering efforts, develop a statewide central user facility to facilitate and promote advanced engineering efforts within the whole state, as well as a comprehensive education and outreach and workforce development effort. When I first came to this workshop, I sort of picked up 2 keywords. One is chemistry, another one is high-performance computing. I felt a little bit out of place because, as one speaker said, his
last chemistry course was in the 1970s. Mine isn't that much later, and also I'm not even sure I understood much of chemistry to begin with. And secondly, you guys are talking about type of work for performance computing. I'm a dumb experimentalist. But what made me feel a little bit better, what eased a little bit of my unease, is in fact the scheme of the SIM program as a whole is curiously coincident with what several previous speakers have talked about, which is a sharing of judicious experimentation with multi-scale computational effort to actually develop models and simulation tools that's calibrated, validated, and that can guide further technology development. What I will try to do is actually give you, this is a fairly large program. I won't do it justice in 20 minutes, and I have about 70 slides. So rather than talking about a lot of details, I thought what I would do is give you kind of a montage-like impression of what the program is about, what are some of the pertinent scientific issues, and some of the potential technology outputs. Again, the program has a fairly developed leadership team and different tasks. I will mainly focus on the science and technology. So first, let me talk about metal forming and pattern replication, give you a little bit of motivation, some research examples, as well as some technology examples. Your aluminum pot that you use at home to cook is a form of metal forming. You take a sheet metal bitumen, you've got a pot, right? The key here is we want to actually extend that technology to the sub-millimeter and to micron scales. And the reason for that, I'll tell you a little story that began 20, 30 years ago. This is the so-called LIDA protocol. Lithography, galvanoforming or electrodeposition, upforming or molding replication. This is a microfabrication protocol developed in the late 70s, 1980s in Germany, where you take deep lithography, define a pattern, do electrodeposition to form a master structure shown in blue here, and then you actually do impression molding or compression molding of the structure to very quickly and more cheaply produce secondaries. This is the so-called pattern replication process. For 20 years or so, this replication process has been used to produce secondary structures in polymeric material, but never in metallic material. The reason for that, and this whole LIDA protocol, I will use this protocol to lead out two, I believe, basic scientific problems that the SIM program will work on. The first one is actually to understand and control mechanical integrity of solid-solid interfaces, in particular of so-called coating substrate interfaces, and how do we quantitatively evaluate the critical stresses for failing the interface, and why is that relevant? In fact, what you can do is you can use lithography to build these nice microscale features, and if you take such a feature, try to do impression molding, as I showed you in the schematic, directly on a piece of metal, say aluminum, what you will find is actually a lot of damage. The pattern you're trying to replicate in aluminum is damaged, and the molding tool of the original feature is also damaged, because here, a lot of aluminum, in fact, bonds with the molding tool and transfers to the tool itself. And people have tried very sophisticated lithography tools to to solve this problem because they thought this was a problem that can be solved by geometry. Meaning, if you put a straight thing into this, when you pull it out, you have a lot of surface-to-surface contact. Instead, what they were trying to do is build tapered structures so that the mold-loading tool, once goes into the material, will leave it more easily. In fact, that's actually not the key science element. The problem is actually solved not through geometry, but chemistry. So there is my one word of ease. Even in this manufacturing endeavor, there is some chemistry involved. In fact, if you make a very thin layer of ceramic on top of your tool, you will see that you can actually directly replicate complex structures in metals with good pattern definition and no damage to the tool. And so here, in order for such coating tools to work, obviously you don't want the coating to fall off. Therefore, the interface between the coating and the tool itself becomes paramountly important. And in fact, this type of solid-solid interface problem is not limited to that particular example. If you go buy drill bits from Sears today, you will find that your more expensive drill bits are actually colored. They have like a gold color to it. That's not gold. That is actually an engineering ceramic called titanium nitride. And when you put the titanium nitride on the drill bit, the life of the tool goes up multiple fold. Again, there are other examples where if you put, for example, a thin layer of ceramic on top of the gear, the contact fatigue life of the gearbox goes up several folds as well. But the key here is that some types, when you put the coating on the gear, the interface survives millions of contact cycles without failure. Sometimes you have massive interfacial failures called spallation. And curiously, for about 20, 30 years, that people have implemented a lot of these so-called engineered surfaces into engineering systems. I would state that this is still largely a trial and error endeavor. The basics is not that much understood. So the desired outcome here is we want some mechanism-based understanding of solid-solid interfacial mechanical integrity such that we can really achieve what's called true material-based design. How do I actually engineer the structure and chemistry of the interface so that it won't fail? In fact, there has been a lot of previous work over the last 20 years looking at this interfacial failure problem. I won't go through all of it. They each have some shortcomings, mainly to obtain quantitative interfacial mechanical response from these techniques. It's actually rather a challenge. What we've done more recently was actually to take advantage of some new nanomachining techniques. For example, use what's called focus ion beam machining. You can manage to machine a micron-sized pillar with the interface region sandwiched in the pillar at different inclinations with respect to the axis of the pillar. In this particular case, the interface is inclined at 45 degrees. Therefore, when you press on the top, you are actually exerting a shear load at the interface. So we can do a series of experiments where you fix the top and bottom, you change the adhesion layer that you put in between. And we know how to characterize their morphology, we know how to characterize their structure, we know how to fabricate these microscale testing specimens, and we know how to test it quantitatively at the microscale to actually get low displacement data. And in fact, here, I apologize, this is a little dark. you will see that when we change the adhesion layer from copper to titanium to chromium, in fact, axial compression from the top invariably induces shear failure at the interface region. And you can, in fact, quantitatively now evaluate what is the critical load to failure in all the systems. One, you can see, obviously, depending on the identity of the adhesion layer you put in, the curve groups are very different. Second, you can see some qualitative differences in the mechanical behavior. Copper is a very ductile material. It comes up. There's a very extended but stable load plateau. These two cases, it comes up, almost fails immediately in what we believe is kind of an unstable way. In fact, first, you can show that this interfacial shear failure stress not only depends on the identity of the metal adhesion layer itself, it also depends sort of on the thickness of the layer. And that I'll talk about a little bit later. Second, there is more recent capabilities that allows you to do actually such kind of testing in situ. I'm not sure you can see it. The screen is actually rolling. Yeah? So we're actually doing microscale testing while we're watching it. What I will call your attention to is what you're going to see is the pillar upper portion is actually shifting to the left as a whole, as the two things shears. So you see stable shear of the interface for a while, and then all of a sudden instability develops, and the thing dies. I won't bother you with this one. Oh my God, this might 20 minutes up. Give me a few more. So I will tell you then that, in fact, you can see from this kind of testing qualitative differences in how material interfaces behave, and that gives you some clues to how to design and these systems. I would also want to say that I mainly showed you experimental stuff, but the computational aspect is intensive. You go from so-called ab initio density functional theory to molecular dynamics, to dislocation dynamics, to finite element. So there is out of the same team, about 50% computational scientists working with the experimentalists in understanding such problems. Okay, I'll flip through this very quickly. Second thing that we do is when you do such impression molding, in fact, you will see that when you mold metals, sometimes the mold itself collapses. And you can build harder molding tools, but that naturally begs the question of what contact pressure, or how do you understand the mechanics of contact? We can actually understand the mechanics of contact first at about 100 to 150 micron length scale. I'll click through this very quickly. Basically says at this length scale, the continuum mechanics remain applicable. As you change the characteristic dimension to microns and submicron, you will see that the contact pressure now has a explicit dependence on the characteristic length. This is not something that's predictable by continuum mechanics. And so that's what's called a mechanical size effect. In fact, such mechanical size effect we have shown depends on the geometry of deformation. Therefore, what we actually need is one for quantitative measurements of the mechanical response in simple and interpretable deformation geometries. Second, we really need calibrated and validated micron-scale models to guide our experiments. We've done some of these work, and I'll skip this. And we have actually compared the data two current scale plasticity models, and you can see there's a lot more work to be done to actually bring the model down to the experiment level. I want to go through some technology examples because the program itself, remember, is on advanced manufacturing. I want to show at least a part of this video. So this is actually a custom machine developed in our labs where you can actually just take a fresh aluminum sheet metal. You can see the roller coming down. This is very much just a normal sheet metal rolling machine, except the roller has micron scale features. Now you see this thing coming out. I'm sorry, it's a little dark. But pay attention to this. You will start to see that the rolled out sheet has actually those micron depressions on the surface. So this is sort of a version of roll-to-roll printing in metallic materials. So that's a potential high-throughput fabrication technique for building small-scale features directly onto metals. You can actually use this type of technology to build, for example, prototype microchannel heat transfer devices that are about as thick as your normal credit card. You'll see water flowing through them, and you can see that the heat transfer efficiency, you can heat this thing up without water to 100 degrees C, where everything's hot. You flow water through. In a couple of seconds, you will see where you have the microchannels. It starts to cool. And in steady state, cold water goes in, hot water comes out, and the whole thing is actually cool. So these are very high efficiency, high capacity heat transfer devices. You can use this technique to actually build two-dimensional surface features that has potentials for enhanced heat transfer performance. And you can actually use the printing technique, for example, to build 70 micron wide, 350 micron deep, so aspect ratio 1 to 5 type meandering microchannel features that you can build into a miniaturized gas center. So, sorry, one more minute. Laser printing. The key here is we not only want to do 3D printing, we actually want to do some materials engineering as to what we can print. Currently, if you do laser 3D printing of metals, you can buy stainless steel powders, you can buy titanium powders, but these are all alloy powders that have been developed for not 3D printing use. So we have acquired capabilities to 3D print, very nice curved chimneys. And what we've done is, first we've done some fundamental measurements of thermal-physical properties of the liquid state. Because in 3D printing of metals, laser beam comes on, and it's a very complex process of the metal powders being melted, resolidified, recrystallized, that builds the whole thing. We want to understand the thermal-physical properties and see whether we can simulate. We use a technique called vacuum electrostatic levitation. You actually put a drop by electrostatic field and oscillate the drop so that the drop oscillation gives you a measure of the surface tension, and the damping gives you a measure of the viscosity. And we've done that in collaboration with NASA Marshall Space Flight Center, and we've generated data such as density, surface tension, and viscosity. And we are actually collaborating with molecular dynamics people to actually try to simulate these physical properties. So that would be an example of the integrated computation. And for alloy design, you can actually, so I'll just go, high entropy alloys are mixtures with basically an atomic soup. What you want to do is use the chemical disorder to frustrate some of the topological order. What you want is is to develop alloys with some disordered solid solution structures that can have potentially better high temperature properties. And to design these, because you're talking about mixing 4 or 5 things in different proportions, if you go through experimentation systematically, it'll take a few years. So what we've done is actually use the so-called calculation of phase diagrams. This is basically a thermochemistry computation tool to actually do some alloy design. And identify potential chemistries and compositions where you have a large thermodynamic possibility for having these so-called single-phase alloys. And in fact, once we've shown that there's some possibilities, we've also shown through the simulation that it is likely in actual solidification, you will have what's called compositional segregation. In other words, the structure you develop is not necessarily homogeneous in composition. In fact, we have actually shown that indeed you have very significant compositional segregation in these alloys, fairly consistent with the Cal-Alpha simulation results. You can confirm these with electron microscopy. And you can even show that using these microscale mechanical testing techniques, that the compositionally segregated regions indeed have different mechanical characteristics. The key is to further understand these materials to see how we can engineer these guys to have some better overall performance. So, what I want to say to you is that we believe the advanced manufacturing program funded by the National Science Foundation brings to our state significant improvements in the advanced manufacturing infrastructure, gives us a motivation for increasing the coupling between experimentation and modeling for high performance computation. And I believe that there are opportunities for the advanced manufacturing team to actually interact with and contribute to other engineering endeavors, such as the chemical process intensification. Especially in the microreactor field, I think metal-based complex geometries that can be built cheaply, efficiently, with variable geometries is actually key to realizing some of these experiments. With that, thank you.
Thank you, Professor Ben. We share the same enthusiasm as him. Hopefully, we're not too much over the time limit, so we are wrapping up the first half of the workshop in less than 10% error. I think we are doing pretty good. 10% even for predictions. Even using high performance simulation tools is considered pretty good, right? So we are going to keep it under like less than 10% overshoot. Our next speaker is Dr. Durai Velan Dakshinamurthy. It is through Durai, meeting Durai, we learned about one more industrial sector that we weren't aware of. We are aware of upstream and downstream. And Durai introduced to another $1 billion piece that we weren't aware of. It's called midstream. So well, we were working there and we weren't aware of it until collaborating with Enterprise Product. Durai works for Enterprise Product and he's going to talk about how they are using computational tools for within Enterprise Products to solve some midstream problems. So, are you ready? You have your slides, right?
Thank you, ma'am. I know the previous speaker started by saying that I was feeling out of place. I also will start by saying I'm feeling out of place because we heard some brilliant presentations before, okay? And then some of the presentations that we have here, from an academic point of view, right? Yeah, from an academic point of view, right, there is a process in place and there is a path to do some research work, okay? But from an operating point of view, right, I'm working for an operating company, okay? And I graduated, like some of the students that are sitting here who did some research work. Then I went into an operating company where we are actually fighting with a lot of day-to-day problems that an operating plant encounters, okay? And so we are always in this firefighting mode. So my presentations may not be as good as the previous presentations. So I'm going to put a disclaimer there itself, okay? And then the second part of the disclaimer is I want to try to, like, whenever I try to give a presentation, I want to pass on some information from industry back to academia, like, what we are looking into right now at an industrial point of view, okay? And then what the students should also look at when they come into the fold of, like, being employed by a company like Enterprise Product, what you will be seeing, okay? So whenever I'm doing a lot of different problems, I try to find a common denominator to put together a presentation as well. So in this one, the common denominator I found was eliminating vibration problems in the industry, okay? So I'm happy, like, one of the presenters talked about a little bit about flow-induced vibration problems, right? So that's a good starting point for me to start, but I will continue from there and then talk about these things, okay? So this slide is getting out of my jail. Whatever that I say, I'm not held accountable, okay? So as Mayank talked about, Enterprise Products is one of the largest US publicly traded energy partnerships with an enterprise value of 52 billion. We are a very large company with a diverse, assets, and our value chain goes from, like, upstream, that is like from the wellhead to the burner tips, and also our things go like in different directions with respect to, like, what we do, what we offer to our customers. We basically purify, transport, store, and market hydrocarbon products. Let's put it that way, okay? And we have, like, 49,000 miles of natural gas pipelines, NGL pipelines. We have a lot of storages which can, like, store NGLs, refined products, petroleum products. And we have a lot of gas processing plants, as well as we have lots of fractionators and so on and so forth, okay? So that's with, like, my introduction to the company, okay? So in this presentation, I'm going to talk about vibration issues in midstream, okay? What are we facing right now, and how are we going to solve these things using simulation tools, okay? So in the first example, I'm going to talk about some compressor vibration issues. Because we are a gas processing industry, we are always going to have to compress the gas so that we can transport from one compressor station to another compressor station. Okay? So we have a lot of gas compressors, and with anything that is moving, right, as a moving part or a rotating part, you're going to have a lot of vibration issues. So I'm going to talk about how we use CFD to remove some vibration issues there. Then we have lots of pumps where we have vibration issues in the pumps too, how we eliminated them using finite element method, okay? And then third, I'm going to talk about flow-induced vibration issues, where we kind of have to use what is called as multi-physics, where we have to have, like, process knowledge, we have to have CFD knowledge, as well as we have to have some structural knowledge to solve the problem, okay? And how we are going to do them together, okay? And then we'll conclude the presentation with some remarks, okay? So vibration is a mechanical phenomenon, right? Oscillations occur at an equilibrium point, and it is desirable for a lot of applications like music, how you are hearing my voice, you need vibrations to be there. But in an industry environment, right, vibrations causes friction, which causes wear and tear, which may result in equipment failures, pipeline cracks, and many more issues. Okay, all the above causes unplanned shutdowns. Okay, from an operating company point of view, right, we never want an unplanned shutdown. We always want planned shutdowns, because you cannot continuously run these plants as well. So we call it turn down, which happens in a planned environment. Okay, we don't like something which is unplanned. Okay, and vibration is one of the major criteria which can cause some unplanned shutdown. Okay. So eliminating vibration issues from design is very critical for safe operation of the gas plants too. Sometimes all these could result in an accident as well. So it is a safety point of view also, we have to worry about these things. So there are many types of vibrations that can occur in the industry. So there, I've classified them into three different things. One is the moving or the rotating equipments, where you come across compressors, pumps, etc. And then there is the second one, which is the flow-induced vibration, which can be caused in many different ways. Okay, one of the slides that previous guy showed is like a multi-phase flow causing a pipe vibration, but it could be an unsteady flow-induced vibration too. It could be a single-phase flow, but it could be a valve opening and closing, which could send some surge waves, which could cause some vibrations as well. Okay. And then it could be internal or external flow caused, which is like vortex-induced vibrations. So if you have a stack that is in a wind, it could actually shake the whole heater, and it could break too. And then there is the third type, which is the acoustic-induced vibration. Whenever a relief valve is opening or a control valve is going out of its operating envelope, you could send these sound waves, which can also cause vibrations in the pipeline. Okay. So today I'm going to only talk about the first three. I know we have very limited in time, and everybody is hungry. Everybody wants to get out of this place, so I'm going to keep it very short. Okay. So the first example that I'm going to talk about is the compressor. This is an axial compressor. It has 15 stages. Okay, and then it has two compressors in a box, basically. Okay, if you imagine, one is called the low pressure stage, and then the other one is the high pressure stage. Okay. And we are always having some issues with this compressor because some of the blades are like getting ripped off during operation. Okay. So before going into detail, I just want to cover a little bit of compressor basics. Probably a lot of people would remember this. For the people who don't, I will just tell you, like whenever a compressor is operating, it always has the safe operating envelope. Okay. For example, for different RPMs here, okay, you will see this operating envelope. Okay, at one end you have what is called as the surge line. Okay, and on the other end you have what is called as the choke line. Okay, so whenever this compressor is going to operate in these two segments, okay, it is going to experience a lot of vibrations within the compressor, and then this could result in blades getting ripped off completely. Okay, and this one completely, like you can see like some deformations here of the blade somewhere, like it's completely taken out of the way. Okay, and then how do we, like whenever some equipment like this comes into our operating plant, okay, and then this happened, right? There is an unplanned shutdown, and this is not a regular item where you can go to a Home Depot and a Walmart and buy and replace that, right? These are all called long lead items. So you need to order them previously, and then you need to have a standby which can run as well, so that the operating plant keeps continuing production. So we do that, but then this has been happening quite a bit. Okay, so what we wanted to do is we want to use some high fidelity tool to analyze what is actually going on. Why is it failing? Okay, even though it is a vibration, which is a structural kind of a physics, but the vibration and the structural physics happens because of fluid dynamics. Okay, so that is why we analyze this compressor using a CFD model. Okay, so just to round it up, what we did with the CFD model, right? We analyzed the performance of the compressor for varying RPM, okay, inlet and discharge pressure conditions, and different fluid properties. Okay, so these curves also keeps varying with respect to different gases. Okay, it's not consistent actually. Okay, so this is the single phase flow passage that we analyzed. Even though you see so many blades are there, right? This, you cannot model the entire thing. You could do it. It would require a lot of high performance computing too. But there are simplifications that you can do too. Okay, there are some models available where you can only model a single flow passage, but can get the whole result as it. Okay, so this is the boundary conditions and what we did with this, and then this would end up giving us results something like this. This is a pressure profile, velocity profile, temperature profile, and density profile. Right? How it is changing as gas is getting compressed. So what does this mean to me, right? This means I can develop operating envelopes for different RPMs, different fluid gases and everything. So from an OEM point of view, operator equipment manufacturer, right, this guy will give us some places where, like, some of the curves we will be able to validate them with respect to our CFD model. So for example, the vendor or the OEM gave us a molecular weight of 28 and 24, where we were able to run the CFD model and then like get these curves validated. Okay. So once we validated these curves, what we did is we went in and did for whatever is in between. Okay. Because our gas properties keeps changing in between. Okay. So once I did that, I could establish what is called as the stability curve. Okay, where I could tell them whenever your discharge pressure is going to go at certain above level, right, your compressor is going to lose its stability and it's going to surge. So that what people will do is people will develop surge controls based on these things actually. And then we did what we will do is we'll open the spill back on this discharge to release the discharge pressure so that there will be a little bit of circulation in between, so that the compressor doesn't go into surge conditions. Or we'll open an inner bleed valve and then we'll let this circulate in between and so on and so forth. Okay? And this has been implemented so far, nothing has happened. So this is a good example from CFD side how we resolved a vibration problem. The next one that I have to show is like pump problem, where the pump was actually vibrating on its own. This is a horizontal vertical pump or a vertical pump, okay, with a motor on top, okay, and these are very much notorious for a bulk weight sitting on top of the pump and then vibrating out of tolerance, okay. And this one is basically we didn't do CFD modeling at all here because the structure was shaking, okay, and we had to operate this pump at certain RPM. We cannot change the operating conditions, but what we wanted to do is, okay, we cannot avoid this RPM at all. So what we'll do is we'll enhance the structure, okay. So for example, this one, the structure that we built was actually having a natural frequency of 59 Hertz, which was very close to the operating RPM of the pump, okay. So we suggested some modifications, okay, and then we implemented those modifications, and you can see this is the vibration amplitude before the modification was there, okay. So we were never able to operate at this RPMs because everything was going out of tolerance. But with the modification, we were able to operate this pump at higher RPMs as well. Okay, that means higher RPM means higher throughput, higher production, higher tolerance. Okay. So the next one that I wanted to talk about is the FIV, like flow-induced vibration. Whenever you are handling any flow-induced vibration studies, right, you have to understand not only the CFD behind it, but also how to transfer the CFD loads onto the structure and see how the structure behaves. Okay, because whenever for example, in this example, the vortice is shredded by this riser, right? If the vortice shredding frequency is going to match the natural frequency of the structure, it's going to resonate and it's going to vibrate. Okay, so we try to find something similar to that. And in multiphysics platform, if you want to do some of these problems, lot of different ways are there. One of the ways is go fully coupled. You do CFD as well as you do structural mechanics, and then you couple both of them and run them together to find a good answer. Okay, that was what the previous speaker talked about. But in reality, you don't need to. Sometimes you may have this decoupled ones that could also give you good answer, and you can resolve the vibration problems based on that. Okay, so let me talk about one of the problems that we had. This is a gas plant, okay, where we are treating for we are treating the gas, and this is an amine treating unit. Okay, so we had a line in between which was shaking like crazy. Okay, and then we had 3 or 4 of these things which are similarly designed, and each one of them were shaking like that. Okay, so first we did what is called as the process simulation, the entire process simulation of this plant, and then identify the boundary conditions that would happen in the line which would create something like that. Okay, then we knew it was a two-phase flow that was going in the line. Before even saying a two-phase flow is causing vibration, you need to validate that there is a two-phase flow in the line, because everything is covered with insulation and everything. You can see them, right? Your pressure fluctuations can show little bit, but then still the process conditions has to back it up. So we did, as per like tool, we did the process simulation, we got the boundary conditions. Then we said, okay, there is two-phase flow, but is all two-phase flow bad? No, not really, right? In an horizontal section, probably a slug flow will be bad, right? For a vertical section, you may have a slug or a churn, which may be bad, you know? So just having multi-phase flow doesn't mean it's bad, okay? So that's why we did CFD simulations here and then tried to find out what kind of regimes will happen inside this line, okay? So it goes from like, different pipe sizes are there, different vertical, and then bends are there, and then so on and so forth. Once we do CFD simulation, we could de-establish all these flow regimes, and we could also get some pressure profiles which we saw in the plant, and then we could try to see if that fluctuations are happening because of that, okay? But without doing structural mechanics, we were able to completely say, okay, this is one of the reasons what is happening here, and we change the process simulations, little bit, so that we will be devoid of those scenarios, and then we resolve these things using, okay? The next one is another example where we had a swinging valve, So the valve was swinging on and off because of a control mechanism, okay? And the control mechanism was going forward and backward loops, and then the valve was opening and closing, and this was causing a lot of pipe movement on the pipe racks. These are all big pipes, okay? And you can see some of the damages that was caused by this, okay? There was a very small line in this entire piping which actually broke, and then hydrocarbon release happened, and then there was a big vapor cloud. We had to shut down the plant, we had to evacuate the facility until everything is resolved, okay? So how do we know, the big question was, how do we know the pipe vibration or the swinging valve caused this thing, right? Because we had structural elements which were there in the pipe, They were like pipe hangers, they were lot of these things that was already put in place, but was this not enough? So that's when we use simulations here, and then we replicate the valve opening and closing. We get this velocity profiles, and then what we do is we get this pressure profiles as well. But these pressure profiles are in the time domain. What we do is we convert them into frequency domain, and then we calculate the natural frequencies of this structure as well, okay? And then if you look at it, one of the frequencies, this 0.69 or 0.7, which is very, very close to the frequency of this valve opening and closing, and this is why this line was moving up and down like that, okay? Then we went ahead and then did a fully coupled simulation as well. What we did is we transferred the pressure loads completely to a mechanical solver, and we identified whether that mode is getting activated or not, okay? Once that mode is getting activated, you will see these fluctuations, okay? This looks like a hula dance, but this is very magnified information, okay? So at the end of the day, all these things, right, can give you some idea where you should be, right, okay? So one of the key things was how will we increase the structural integrity right now, okay? We already have some U-bolts and everything. We went ahead and did a lot of other simulations just to tell them where and all they need to add support, what type of support needs to be added, what type of reinforcements need to be added so that it could be controlled in future. So when we do that, your natural frequency went to very high, which is very, very high than what it should be, okay? You can ask, why didn't you work with the valve? The valve has to be in an automated mode, okay? We did decrease the response of the valve, how it is opening and closing, but still we want to activate the valve on and off based on the process simulation. That is the reliability concern, okay? That's why we had to work on the structural side to fix this problem, okay? So with this, I would like to conclude, vibration is definitely a major problem. One needs to understand the flow features and also understand the structural dynamics of the structure to resolve vibration problems. Ideally, one would solve all problems in a fully coupled manner. However, this is computationally expensive. Most of the time, we do have a lot of HPC, but still, sometimes you don't have the real time to sit around and do a lot of other things. So you may have to simplify your problems to a point where you can make good engineering judgment calls. Okay? In some scenarios, that's exactly what I told. And then finally, I presented some scenarios wherein, we resolved them in very different ways, right? Sometimes we use CFD, sometimes we use structural mechanics, sometimes we kind of couple them together fully, sometimes we kind of couple them partially, and so on and so forth. Sometimes we have to use a thermodynamic tool or an Aspen or a Promax to resolve our problems too. Okay. So the showcase problems shows the value of using high fidelity tools in eliminating vibration. Okay. Any questions?
Right, and precisely on time. So I would request audience, though the food and everything has arrived, we have just one presentation left, so we might overshoot it by like 10 minutes or so. If you be patient, we will be able to finish the first part of the EPIC workshop before lunch. So let's have one more presentation while the food is waiting for you outside, rather than you waiting for food, right?
So I've got my timer on my phone. I will do mine in 10 minutes. Back on time. 10 minutes. I'm going to make sure.
Okay.
I also have a flight at 1:43, so I will be on time.
So Mr. Nick Ivey works for IBM, and while we have during the first half, we have learned a lot about how the future of computation is going towards exploration, going towards machine learning, deep thinking, Internet of Things, and IBM as a partner, also with the NNMI effort and all, have been helping some of the groups getting into cognitive computing and also what we're talking about IoT, Watson type of data engine. So, yeah, I'm hoping that, please talk about Watson IoT.
So, good afternoon, everyone. Thank you again. My name is Nick Avey. I'm with IBM. I'm in a division called the Watson IoT. I'll get into what that stands for here in a few minutes. This division has been created by IBM about 11 months ago, and I'll go through exactly why and what the significance of it. As I said earlier, I have about 11 slides. So, and every speaker has done a great job. Thank you all for coming and sharing. I'm definitely the outlier here because I'm not a chemist or a chemical engineer or electrical engineer. I'm a sales leader. So there will be no formulas, I guarantee, up on any of these slides at any point in time. So I wanted to kind of, and first I want to thank LSU for inviting me to spend a few minutes. We've, Dr. Tyagi, Dr. Kumar, and Ram and others have been working with IBM on a variety of areas, not just this topic, but a partnership for a number of years between IBM and LSU. We started talking about analytics and predictive analytics in the last year or so, and how it could be applicable in a variety of areas in research and others for the university. So again, thank you for the opportunity. I wanted to kind of just spend a first couple of slides here telling you about what predictive analytics is, what Internet of Things stands for and what it does, and then drill it down into kind of some use cases, specifically with the chemical and petroleum industry, an upstream ESP use case, and what a executive in a petroleum company might look at for predictive analytics, what an analyst might look at, and so on and so forth. So, but to back up and give you a 2-minute high-level overview of what in the world is IoT and what is predictive analytics. Predictive analytics has been around for a very long time. It's simply applying mathematical algorithms against the data set to predict an outcome. Pretty simple stuff, right? We define predictive analytics as either predictive maintenance. We're going to predict an outcome of an asset that's really important and notify when to do something about it, or predictive quality. We have an asset that's making something, and we really want to know if the quality is degraded or whatever they're making. IoT, does everyone know, just raise your hand, what IoT stands for? Okay, good. So I travel around every week. I'm in an airport somewhere. I'm talking to somebody or my neighbors, and I either get, at this point in the inflection point of IoT, of course I know what IoT is, to I literally never heard that phrase in my entire life. What are you talking about? So Internet of Things, and you can go through and see all the different definitions. I found one that I really liked was simply transforming a physical object into a digital data product. So transforming a physical object into a digital data product. Once you do that, by slapping a sensor or a device on that physical object, it can behave just like other digital data products. You can know what the usage is, what the status is, the location, if it's doing well, if it needs help, it can collaborate, it can be intelligent, it can be autonomous in some areas, and you can be really, really good at predicting things now that you have sensors. And so what's changed? Why has IBM formed a group called IoT? Why is SAP and Microsoft and GE and everyone else done the exact same thing? There's a lot of savings, revenue, top-line revenue growth, and operational cost reduction by being able to listen to those sensors that are talking to for the very first time and being able to predict what's going to happen and how those things. And so I think of IoT, the significance of pervasive connectivity, embedded sensors. Those things have become very, very cheap. The cost and performance ratio of putting sensors on physical objects is what's literally changed. We've had analytics for a long time. You've probably seen more big data presentations than you ever could stomach. That's what's different, is being able to now get a whole new data set that is incredibly large and incredibly meaningful and apply the same level of analytics to those. So that's one. Just some high-level numbers. There's 12 billion sensors right now on physical objects. 12 billion. There's going to be 20 billion in the next 2 years. The market is, for revenue, is $3 trillion by 2020. So just think of your house. Your light bulbs are going to be talking. Your refrigerator is going to be talking. My wife said I can get on a scale in the morning and notify my refrigerator of how it should behave with me throughout the day. Everything is going to be communicating and talking, not just in your home, obviously, in a very asset-intensive industry like chemical petroleum. These assets are very, very expensive, very important, and downtime is very expensive. So we're able to monetize that as well. So one of the examples, if I can do a laser finder, is I was talking about operational cost reduction within chemical petroleum again. The other interesting thing I want to bring up is that's kind of the no-brainer, if you will. Wow, these assets are important. They're talking for the first time in a way we've never been able to do. Let's apply analytics and make sure there's zero downtime, or we know 2 days or a week ahead of something versus a time-based monitoring. That's kind of a no-brainer. What's really interesting is half the folks I speak with, and I didn't think I actually introduced myself, Nick Avey, I mean North America sales for IBM in this space. So I have a team of folks that are talking in literally every industry across North America. Half my time is in this area within IoT. And again, I said that $3 trillion is the revenue opportunity. It's not just companies like Microsoft or IBM that are going to tackle it. It's companies that have had legacy data or legacy knowledge in one industry, secret sauce, if you will, and now being able to embed or OEM, one like IBM's model, into whatever it is their service they're selling or whatever they're producing as a product, and now applying analytics as well. So literally half the time I'm out talking to folks, it's about their new top-line revenue growth and not their line of manufacturing plant for doing something better. Okay. Here's how this kind of works. Again, as I said, and I'll try and do this really quick here. Assets are now producing data. We're able to connect to and apply analytics. This is an example. I'll get a much bigger screenshot here in a second. This is an executive view of an ESB. The so what is, again, the basic meat and potatoes, reduce unplanned downtime, lower maintenance costs, extend the asset of a life of an asset, operationalize, optimize maintenance schedule, so on and so forth. Specific to chemical petroleum, here are the areas that folks are looking at applying this type of analytics to. Again, upstream, midstream, downstream. Every asset, every physical device that now has a sensor on it, now is applicable. One of the examples I'll be going over here in a minute is this. I'm going to give you a 30-second on kind of my point of view or IBM's point of view on what you should be looking at whenever you're considering this type of endeavor. And spoiler alert, it's areas that our company is really good at, so I am biased. But when you start to look at analytics, the significance of now having billions of devices now talking is you want to be able to ingest this unstructured content, this unstructured data, into a way that's not, completely overtaking your existing IT department. That probably terrifies IT in every area. Oh my gosh, I got my hands full right now. Now you're shooting millions of data rows at me every day on something that's talking that I can't understand. So you need to be able to ingest this data in a way that does not involve IT at all, optionally, that can be open to a variety of protocols. So you need to have a partner that understands not just proprietary protocols, but literally every physical sensor, be able to ingest whatever data type or SCADA system they might have that's talking, be able to store it very optimized. You need to have a visualization layer, which I'll show you in a second. But the significance of it, kind of the theme of the day, is innovation with data, the building models. You need to be able to very quickly be able to spin up a new model without doing programming and simply have data scientists or folks, analysts, be able to grab data which they've never had before, compare it with data they know really well, build a model, and within a half hour have a whole new approach and a new results that is something they never knew before. It can provide more insight. So it's the ability to create new models very, very quickly on the fly. The other significance is be able to have a system that can have different personas. So this same, I'll call it analytics platform, I won't get into the tool names and everything else, as I said, across all industries, and it's on all different departments. But this is specific to again, chemical and petroleum. It applies the basic, again, analytics, decision rules, dashboarding, but this same platform, if you will, should be accessible to executives, to analysts, to the person that's proactively ordering a maintenance repair on whatever it might be. So here's an example of ASPs. Everything I've already talked about. This is data. This is new data, right? Never been had before. Video, text logs. Being able to ingest all that data, combine it into a predictive model, and apply it to something that you know. Here's an example of some kind of a high-level value prop, situational awareness, decision support dashboards. Again, it's insight onto a new model. So this is an example of what a persona would be for an executive. And they're simply just looking at, I'm logging into a system and being able to see what's high risk, medium risk, low risk. This is pump details. They're able to very quickly be able to view from an executive dashboard. Here's what's going on in my environment. Now you drill into an analyst perspective. You've got historical data. You've got a much more deep presentation layer of types of information an analyst would like to know. It's not super clear, so I apologize. But this is my equivalent of the engineering chart that you've seen before. It's something's happened here in real-time series comparing to the historical data, and it's alerting an analyst to do something. Then it sits on to someone who actually do an installation. They're actually been connected to an enterprise asset management application and being able to order an exact part. Again, this is all proactively. This isn't a sensor saying, hey, I broke 5 minutes ago. This is a sensor saying, you know what? I'm exuding the exact same behaviors that every other sensor like this, coupled with all the history data we've ever collected, now says in 2 weeks I'm going to fail. So predict that, and whenever you're out next to this other physical device, which is right next door to it, a week from now, bring this part with it and make sure that new device never actually goes down. That's the theme of it. I've got 5 slides just about examples of kind of the value prop we've done within oil and gas. This is in Australia, I can't use actual names, but same value prop I've been discussing. Uptime. This is kind of an interesting one where it's optimize where you're putting physical assets in a petroleum facility. Drilling delays. We look at corrosion. Is a very common use case. And this last one's an example of a Canadian oil producer looking at steam. So I guess the so what is, this is one example of in one industry. Again, all industries are looking at the same kind of value prop of being able to collect information from sensors that never existed before and provide predictive analytics. That's it.
Let's thank all our keynote as well as all the industry and university researchers for really providing us a thought-provoking epic workshop for 2016. And there is going to be an afternoon session for the hands-on tutorials on CPU electrics processing. So we have not signed over 10 open slots or 2 hours of session for them. Of course, there's a question by you.
Oh,
Yes, right there.
hi.
Software that really software should be very adapt to the new the new computer. If not, there is nothing more, and we should not get done due to the screening, due to the local thing, due to the time scale in terms of interpretation. So I think you should mention your presentation where the data analytics and HPC should be coupled.
Thank you for sharing that. I mean, what's interesting in IoT is that I didn't talk about sensors at all. I didn't talk about a whole host of things around curriculum analytics. There's an ecosystem, and our approach is what we're finding is everyone is partnering right now across the board. I'd like to talk to you in my card whenever we're done. But we're partnering with sensor companies, or partnering with software companies, we're partnering with hardware companies, so on, and with consulting companies. In every industry, what they might have is a very specific niche or legacy insight that then they can solve different types of problems.
So, for example, with that should be coupled with the computing facilities with the
Hi.
What are you doing about security concerns? I mean, certainly talking about the oil and gas industry, you know, if I'm going to put one of these things in my plant, I don't want somebody else to be able to get the data. I certainly don't want somebody to be able to monkey with my sensors and cause trouble. And, you know,
So there's
recent
something
internet
called-
attacks have shown that Internet of Things devices tend to be very insecure. So how are you
Absolutely,
going to address
that's the Achilles heel right now of IoT is the actual real ability to hack and perceive the data. So what we're seeing, a lot of organizations are doing some edge, doing analytics on the edge, and not having connected it all to the internet at all, not having connected the IT system at all, but having a line of business running independent with edge devices that basically have no ability to be hacked. And so I would not ever recommend having anything, a sensor connected to the internet. Now, the ingestion data point, we have something called the IoT platform, which does collect all this unstructured data and has its own security system built into it, but everything's still happening. So I think the safest guard is don't have it connected to your IT department, don't have it connected to anything in the internet.
Has this ever been implemented in like process control for a plant?
I don't know. Find out for you. Either your email will send you that. All right. Thank you very much.